today a Spanish mathematical Olympiad. Let's rock and roll. Okay guys, so today a 2012 Spanish mathematical Olympiad. We are supposed to find all m and n that are natural numbers such that n plus 1 to the power of n is equal to 2 times n to the power of m plus triple the n plus a 1. Okay, so well, let's maybe do it this way. This problem I would like to solve. I would like to show you guys the solution, and then I will tell you at the very end of this video how to actually approach this problem so that you would ever think of this solution in the first place, for God's sake, because it's pretty complicated. Okay, so, well, I would like to break this problem into two cases. First of all, I would like the first case for m being equal to 1. Okay, so for m equal to 1, what am I gonna get here? Well, n plus 1 to the power of n is supposed to be equal to double the n. Well, n is a 1, so not writing any power there, to plus 3n plus a 1, but this entire thing is just equal nicely to 5 times n plus a 1. Well, we see that this thing is probably not gonna have any solutions, because here we've got an exponential, here we've got a linear function in terms of n, so well, this guy on the left hand side is probably gonna be much is gonna approach much bigger values than the guy on the right hand side. However, well, we could prove it using induction, all that stuff, but let's maybe do it using calculus, because I just like this stuff. So for n equal to 1, for n equal to 1, what we're gonna get is 2 to the first is equal to a 6. Well, that's not really true. For n equal to 2, you're gonna get well, 3 to the power of 2, which is 9, which is equal to 11, which is also not true. And then for n being equal to 3, what we get is, well, 64, I believe. Yes, 64 is supposed to be equal to 21. Okay, so we see that, you know, above this barrier of n being equal to 3, our n plus 1 to the n is gonna just skyrocket up, and our linear function 5 times n plus 1 is just gonna, you know, keep grinding linearly for the rest of the eternity. And so we see that there will be absolutely no solution after crossing the point of no return, which is n equal to 3. There are also no solutions before crossing that point, so there are no solutions anyway. Well, how do we prove that there will be no solution after crossing the point of n equal to 3? Well, we could just calculate, let's say, the derivative of both of those functions. We see that the derivative of the function on the left hand side, which is n plus 1 to the power of n, is a lot bigger, because it's going to be n times n plus 1 to the power of n minus 1 times 1, because of the chain rule, and the derivative of the stuff on the left hand side is going to be just a 5, and so we see that definitely the guy on the left hand side is gonna be greater for any kind of a value of n that's greater than or equal to a 3. Lovely. And so we said the guy on the left hand side is just gonna be, you know, gaining weight, gaining value faster and faster. And now for the first case, well, for the second case, I would like to see what's gonna happen when m is greater than or equal to 2. Okay, so when m is greater than or equal to 2, the nice thing you could kind of see here is that double n to the power of m plus triple n plus 1 is going to actually be congruent to triple n plus 1 modulo n squared. Well, why is that so? That's because this m right over here is greater than or equal to 2. And so this n to the power of m is at least n squared, and so we can just go on and factor it out from this double n to the power of m. Okay, so, well, that's pretty lovely. It means that we can kind of go on and check what the left-hand side of our original equality, so this guy n plus 1 to the power of n will be congruent to modulo n squared, and maybe it will give us some important intel, yes? So let's just say that this stuff we will denote as the right-hand side just for the sake of clarity, and it's going to be our left-hand side for the sake of clarity. So we see that our right hand side is equal to this, congruent to 3n plus 1 modulo n squared. Now our left hand side is going to be equal to, well, that was n plus 1 to the power of n, but by the binomial theorem we can say that's going to be equal to the sum from a k equal to 1 up to n of n choose k n to the power of k. And now, well, evaluating that sum a little bit, is going to be 1 plus n choose 1 times n plus n choose 2 n squared, and then just, you know, a bunch of dots, and then n choose n to the power of n. So we see that, well, this guy is going to be divisible by n squared. Well, all of the stuff between n squared and n to the power of n are going to be divisible by n squared, definitely. The nice thing is that n choose 1 is actually n, and so this entire thing is going to be n times n, which is n squared, and so it's also going to be divisible by n squared. And so what we see at the very beginning is that this entire n plus 1 all to the power of n is going to be congruent to 1 modulo n squared, because 1 is the only term in this entire sum that's not going to be divisible by n squared after, well, multiplying out this n choose 1 times n. And so we see that our right hand side, or maybe let's say our left hand side, is equal to our right hand side. Well, that's what the problem statement says. This means that our left hand side also will have to be congruent to our right hand side modulo n squared. I mean, if two numbers are equal to each other, they just cannot leave a different remainder upon division by any kind of a number, yeah? And so this means that our left hand side, which is congruent, remind you, to 1 modulo n squared, is going to be congruent to 3n plus 1, because it's congruent to the right hand side modulo n squared. And so this means that 1 is congruent to triple n plus 1 modulo n squared, but that's just triple the n being congruent to 0 modulo n squared. Well, if triple the n is divisible by n squared, well, what does that mean? Either n is gonna be equal to 3, because, well, then 3 times 3 is congruent to 0 modulo 3 squared, or n is equal to a 1, because then 3 times 1 is congruent to 0 modulo 1. Perfect. So we have only two solutions, n being equal to 1 and n being equal to 3. Those are the only solutions for m's that are greater than or equal to 2. Remind you, there were no solutions for m being equal to 1. Lovely, so those are our just about only two candidates for the solutions of this Diophantine equation. So let's try and consider them one at a time. So first of all, we would like to consider the first case. So let's say n being equal to 1. Well, we're gonna get then n plus 1 to the n is gonna just become 2 to the power of 1, which is 2. And then 2 times 1 to the m is just 1, so that's gonna give us pretty much just 5 plus 1, which is 6. And so is 2 equal to 6? Well, not at all, it's just a contradiction, so we don't really care about this case anymore. Now the second case is gonna be for n being equal to a 3. Well, what's gonna happen then? The left hand side is gonna be equal to 64, because that's 4 to the power of 3. Is my maths correct? Yeah, I think my math's correct. I mean, I'm not good at math, so it might not be. It's gonna be equal to double 3 to the power of m plus 9, because that's 3 times n, and plus a 1. And so now we just get that 54 is equal to 2 times 3 to the power of m, and so it means that 3 to the power of m is equal to 27, which nicely tells us that m will be equal to 3. And so we managed to find an m such that it will satisfy our equation for n being equal to 3. Well, remind you, there were no solutions for there were no other solutions, and so it just nicely tells us that the only solutions are m and n both being equal to 3. And now, how the hell would you come up with this solution? Like, okay, yeah, it is nice, it's pretty smooth. Those modulos, those n squares, it's lovely. But how the hell would you ever come up with this thing on your own, for God's sake, especially when you're just giving a sheet of paper, a pen, and you're just trying to get your points on the Olympia. Well, the nice thing is that, the nice thing to think about is always when you have a Diophantine equation, it is best to just check the divisibility of both hand sides. Because one of those hand sides, probably in any like kind of Olympiad problem, will be not divisible by something that the other will be divisible by, or they will give a different remainder, or as in this particular case, well, they would leave different remainders, and then we can just say that those remainders are going to be equal, getting, well, our desired solutions. And so always just try to get your hand sides. We always try to get all of your expressions into forms where it is clear that, well, there will be some kind of special number that this expression will leave a nice remainder upon division by. So for example, I did do, oh yeah, now purple is a nice color. I did, how do you say it in English? Oh man, I did calculate n plus 1 to the power of n using the binomial theorem to get that it is gonna be congruent to 1 modulo n squared. And probably by noticing this thing on the Olympiad, I would be able to think, oh, mate, well, that's nice, because if m is greater than or equal to 2, well, then the right-hand side is going to be congruent to 3n plus 1 modulo n squared. Well, that's a nice thing. Then I would probably go to the first case, so m equal to 1, just, kind of rub it off and say, yeah, there are no solutions. Screw it, I don't really care about it. And then I would come back to the case of m being greater than or equal to 2, just say that those two remainders are going to be equal to each other, just as I did right here, and then just get those n's. So once again, how would I actually approach this problem in the first place? How would I get this kind of a solution? I would first of all go on, so what I did first of all, is I went on, I multiplied out this n plus 1 to the power of n using the binomial theorem. I noticed that all of those things are divisible by n squared, but yeah, you have to notice it, but just show me an Olympiad problem where you don't have to notice stuff. That's the sad reality, unfortunately, of math competitions, yeah? And then after noticing that, you just kind of break your problem down into two cases of m being equal to 1 and m being equal to 2. Yeah. Okay, so I really hope you enjoyed it. I really hope you got my explanation right. If you still don't understand how I came up with that solution, just hit me up in the comments. I will be glad to A, reply to a comment, and B, if there will be a lot of those comments, I will just, maybe record a short about it in the future to just make it clear for everyone. Okay, so now thank you very much guys for watching, and hopefully see you in the next one.